Autonomous multi-floor exploration is a new behavior for ground robots that requires travel between different elevations in an environment. One way for robots to transition between floors is to traverse stairways, and many robotics platforms are capable of doing so autonomously. However, existing methods for stairway detection and localization serve only as a trigger for immediate traversal by the robot. In an autonomous exploration scenario, we desire a system that can detect, localize, and anchor stairway objects to the map it is constructing, such that the path planner can later direct the robot to traverse the stairways it discovers. We propose a system for detecting, modeling, and localizing stairways. It consists of a detector that extracts stair edges from depth imagery, and a modeler that aggregates the extracted edges from multiple observations and estimates the parameters of a generative stairway model. Lines of depth discontinuity are located in depth imagery, then filtered and clustered to enforce the physical constraints of the step edges of a stairway. A point cloud of observed stair edges is then extracted from the depth data. These edges are then aggregated into a single point cloud over multiple observations. We assume that mapping occurs independently, and we rely on the robot's estimated pose to approximately align the observations. After several observations, a generative model is fit to the aggregated point cloud. This model consists of an inclined plane constrained by a bounding box. Step edges that are well supported in the cross-sectional projection of the point cloud are used to infer the step dimensions. Statistical outliers are removed during each model fitting. Repeated observations induce further refitting, and the model converges with subsequent re-estimations, typically within about 30 observations. Over all of our ground truth trials, step dimension estimation is accurate to within 2 centimeters, while the stairway pitch is accurate to within 3 degrees. We can accurately localize a detected and modeled stairway in a large map, providing the necessary functionality for multi-floor exploration. Despite the limitations of structured light sensors such as the Microsoft Kinect in outdoor environments, we found that in many circumstances, even the compromised depth data in outdoor settings was adequate to build an accurate model. Our system is robust to false positive detections, since they are removed as statistical outliers in the modeling phase. However, our detector has also proven to be highly accurate, with only a handful of false positive frames over many hours of testing. Our proposed system is capable of accurately modeling and localizing a stairway from multiple depth image observations. This system represents the first step toward fully autonomous multi-floor exploration.